Hello all, welcome to my channel. Uh, in this video, we will be discussing about the Iceberg Geo data type, which is a new data type supported in Iceberg v3. This is continuation to the series we are doing on Iceberg, and this video we will discuss about two data types for geography and geometry, which has been added. There is one more data type, specific data type, which has been added called variant. We will have another video for discussing that. So let's get started for this one. So what has happened is that in generally in the geospatial field, the the file formats and data types are different than the tabular data, traditional tabular data that we are used to. For example, uh, the data that we have CSV or Hive tables, everything. So those are different than the geospatial data. Geospatial data has different file formats like shape file, raster data. Then we have TIFF file formats. Then we have GID file formats. So there are different file formats which are there for a specific use case. So as it happened with the tabular data, that the different file formats, like everyone started, every other file formats were standardized in a sense that and that gave birth to a Parquet or other open table open file formats on which we built open table formats and making them data, making those files behave like a table. But that didn't happen for geospatial data because it was different, so people didn't focus much. But recently, now what has happened that there is an unification process going on where we want to unify the traditional tabular data analysis with the geospatial data analysis because that is very much important. And that's where this Iceberg's V3 support is playing a crucial role because with this native geospatial data type support in Apache Iceberg and Parquet, we can have engines, means we can in process data or this geospatial data with engines like DuckDB, Apache Sedona, Apache Spark, Databricks, Snowflake, or BigQuery, and this will help actually in unifying the analytics for both traditional data as well as geospatial data. For example, let's say we have uh, population or census data for a particular district in a tabular format, but we have the flood related data for that particular district in let's say geospatial or some other data. Unless we combine them, we won't be able to notify which families needs to move from one location to another, or which type of houses they should be building for their home to be secure or to be flood proof. So that kind of analysis we can do once we have this both tabular and geospatial data uh, being processed from the same engine, because we will have that same both of the data in same place, and then we can join. For example, we read the flood related data in a geospatial format, and then the same on the same engine we use the population data or census data, and then we combine it and then notify the users that what they have to do in case of a flood. So that is very much interesting, which is coming into Iceberg. And Iceberg has two types of geodata which is supported as of now. One is geometry type, another one is geography type. So geometry type is, as in the name suggests, geometry is generally of the planar objects. So the geometry type represents the spatial objects in planar space using Cartesian geometry like XY coordinates, latitude, longitude. So that kind of data is stored in this geometry type, and here the distance and area measurements are performed on flat surfaces. So that's what differentiates geometry with geography data. Where the one geometry data type is planar, and it works on flat surfaces, while the geography data type, which is spatial objects on the ellipsoidal surface, means the if you see in this picture, this is the geometry data which is on the flat planar surface. We are taking the distance between these two, but that is not the actual distance. Let's say if a plane has to fly from this and this, if it follows this straight line, it will be a very long distance. If we follow the earth's surface, which is spheric in nature, or we can say uh, that it is ellipsoidal in nature, that will save fuel, as well as it will be lesser distance. So that's why in the satellite or aviation navigation we use geography data type, which follows the Earth's curvature and ensures that spatial operations like distance and area calculation reflect real world geography rather than simply giving a straight line. For example, let's say if we have what if we have to find distance between, let's say, a point in a valley to the top of a mountain? It's if we simply look at straight line, that will not be the right what you call measurement. Because we have to uh, if we are building a road or something on that curvature of the what you call earth, sorry, the mountains highs and lows, then the distance will be different. So that's why this geography data type is very important. And as we were saying, there are few differences between geography and data type. We have already discussed one defines features on a sphere versus a plane, because it is based on the coordinate system. The distance measurements happens in sorry, geography data is based on the surface area. Then that's why we not surface area but on the surface contour. So the measurements are in meters and the coordinates are in degrees. But in case of geometry data, it's the coordinate values are defined by the spatial reference system itself, and the measurement of those operations are. So, for example, if we are talking about straight lines, we measure that straight line with a degree itself rather than converting into meters. And also, segments are interpreted as geodesic arcs on the Earth surface in geography data, but while this is segmented on a flat surface of Earth. So that's where the geometry data comes into picture. And there are different edge interpolation algorithms, which is I mean, in this interpolation algorithms actually decide the accuracy of the spatial orientation. Uh, so we have planar, which is straight line edge, spherical, which is geodesic curve as the edge, and then we have others like Vincenti, Thomas, Endoyer, Carney. These are certain other edge interpolation algorithms, and this is important because the implementation, whatever is needed, like for example, if the geography data type is there and we want to use certain algorithms. So that should be consistent because uh, if we are reading this data from different engines, if the implementation of those calculations are not fixed in terms of algorithm, then the different engines will interpret as differently. So that's it becomes essential for Iceberg to implement a certain specific algorithm for edge interpretation. Encoding this geodata type supports different types of encodings like WKB or WKT, and uh, it will support I mean, like geo enforces a longitude and longitude coordinate order aligning with the standards used in GeoPanda, Sedona, and Google Maps. So it is pretty much following the same GeoS standards. Uh, Coordinate reference system, like there are two which are supported as of now. One is CRS, another one is ProjJSON. So this is one other thing to know. Lower bound and upper bound calculation is something which is very much important to note, is that because Iceberg follows this concept of maintaining max, min, and other stats of a file. Similarly, we will have to I mean, Iceberg calculates certain bounds, and those bounds are western, easternmost, northernmost, and southernmost extents of the spatial objects, and the latitude and longitude, which is where is there present, those are also used as an boundary. Now coming to the operations, these data types will support all the DDL, DML, and DQL operations which are generally present for other data types, but it will have some special functions which are specific to these data types. For example, ST intersects, ST contains, and ST distance. These are different filtering. These are used for filtering and analysis, other analysis. So this function is available. As of now, there is no concrete implementation for the Z order, but we can use S3 spatial index, which Uber uses, or we can use Hilbert curve method for Z ordering the geospatial data. Compaction, we can do the compaction as we do it for other non-tabular data, tabular data. The same way we can do compaction here as well, but only thing that has to be maintained is that while we are doing the compaction, we should be recalculating the spatial stats, so that it remains the query pruning and other things continue to work after we merge as well. It supports these data types are supported for any REST catalog which is implemented. And then if you see, these are the certain operations on this new data type. So we can create a table. So we have to just give the column type as geometry. If we want to have geometry data type, then we also have to provide a table properties called format version 3, because it is only supported in Iceberg spec 3. So that is mandatory. We provide that. As I mentioned, there are different packages. GeoPandas is one package. Sedona is another package which allows distributed processing of geospatial data. So what we are doing in here is we are creating a Sedona data frame on a geometry data type, which is line string, and then based on this, we are creating two columns. One is ID, one is geometry, and then we use this function called stgeom from text, which is this line string, whatever is there, it will just calculate that and then return. And we are just writing it to the table that we created in here. So this is first insert. We inserted two rows. Then we can do the append as well. So again, we inserted the two rows in append mode. That's why mode is append, and then it will write it to that particular same location. Now what we will do is we will append a line. Again, these are C and D are also lines. So E and F we also insert and see how it goes. It will work as it is, because this is also just an appending to the same table. Now we can do delete. For example, whatever polygon that we have created, we can say delete from this table where the ST. There's a function called ST crosses based on the geometry, and then if we give the geom from WKT method and then pass the polygon that we have created, it will delete all those lines which are touching those polygons that we have mentioned. So this is how we delete an object, delete a geometry data type. Then we can also do time travel. This is all similar to what other things do. So we can just list down on the all the snapshot ID and timestamps, and then we can run this query to give system version as of. So when we give this, it will give the version ID. We can pass that version ID and see a particular state of the particular files. We can also do upsert operation the same way that we do it for other. Only thing is when we do comparison, we say update uh, insert ID, geometry, and everything. So everything remains same as how the merge SQL works. Merge syntax is there for others. We can do in schema enforcement. For example, here if we define this schema where we say we have one column X, then we have one other column for ID, and then we have some geometry data type. And let's say if we created this, but this we have created with three columns, and previously the table had only two columns. If we write to that table, it will throw an error saying that okay, we can't insert because the schema is different. So if we want to do a schema evaluation, we will have to change the table, what you call alter table, and add this column. So now we will have a new schema, and then we can override or append new data that we created here. And now the newer schema will have three columns. So that is for the schema evaluation. And then we also have compaction, similar to what we do for others. We can simply say Iceberg system rewrite data files, and sort while doing the sort order, we can say Hilbert based on the geom data that we have. So that is again something we can do with these new data types. There are certain functions, for example, st point, which is nothing but it creates geometric point objects from latitude and longitude coordinates. So we can do that. We have contains. So based on these two geometry data types which we provide, we can find out whether this particular thing is inside this or not. For example, we can say customer ID where ST contains flood zone and customer location. So what we are doing is the flood zone is part of this or not. That means this flood zone contains this customer location or not. Similarly, we can do intersect. It is with a simple to check if two geometries share any portion in space. So select we can do intersects, and let's for example properties geom versus wildfire zones. So what it is saying that if a certain person holds, let's say, certain property, is that property part of any wildfire zones? That we can find out using this intersect method. Then we have st distance, which is nothing but to calculate the geometric distance between two geometries, which is again we can say select here we are selecting based on the latitude and longitude, we are finding the distance. We can also do a buffer, so create a buffer zone around a geometry, that we can also do. So we can give st within, so it will create a boundary, and then we'll say the buffer we want to do is, let's say, customer location based on, and we are saying that okay, new store, whatever store we have as a 5 mile radius, that we are creating a buffer, so something like that. We also have use cases like as we in here also we saw some use cases of these data types, like we can identify high risk properties within a flood zones, or we can enrich customer data with property attributes, like this is important for companies like DoorDash or booking.com, and this is important for companies, let's say any agriculture company, if they want to know that whether certain properties that we have for certain customers that they are managing, is it that flood prone, or what is the probability of flood coming to in that. So based on that, they can do some suggestions to that user. So that is something, another use case that we can have with this geometry data type. And why this matters is these data types will now have, because it is integrated with the lakehouse system, it is efficient to storing. We don't need a separate system altogether. Better governance because we can leverage full SC transactions of Iceberg, and also faster insights because we have like those indexes that we were talking about, H2 index or H3 index or S2 index, or file level skipping based on certain what you call attributes that we have, or min max that we have calculated based on a spatial data. We can do faster analytics as well. So these are some things that we will be able to do with this Iceberg new geometry data type. So that was it for this video. If you like this video, like you can share this video with your friends and spread the word. That's it for this video. Have a nice day.